Well, in this video, I will sketch the implementation of perception training algorithm use basic Python functions. I have already done a little bit data preprocessing stuff, which I will share the code in the course materials. It's not complicated. The final result is now we will use the iris dataset as an example, which as we have learned in the first coding tutorial, that we can load it from the built-in datasets from the scikit-learn library, and I will only choose the first and the second class, that is Satosa and Versicolor, for to construct a binary classification problem, which is what the vanilla, by vanilla I mean by the most straightforward perception algorithm does. What need a little bit attention is in the original data set, those classes are labeled as 0, 1, and 2. Now we have only two classes, and to fit the perception training algorithm, we will label the classes use -1 and +1. Also, we need to assemble the data so that each data sample will have an extra attribute that is constantly 1 for every data sample. Therefore, we will include the bias constant of linear model in artificial weight for each sample. So this is what the data looks like as our starting point. Let's execute this. So this is none other than the iris data with one attribute, constant one attribute in each sample. So now the data has 5 dimensions, and you can check the shape of the data array. We have 70 training points. The suffix homo refers to homogeneous coordinate. It is a mathematical term, which means when you try you represent a vector with a trailing 1 in the vector, so that you do not need to worry about the bias. Similarly, we have done the same to X test. Let's look at the Y train. So they are -1 and +1. That is our data. Oh, by the way, we now use array manager to contain our data. If we check the type of the variables, we will find they are NumPy n-dimensional arrays. I hope the necessity to learn a bit about array operation won't burden you too much in terms of programming. We will introduce those skills step by step. For now, you only need to know we have import a library called NumPy to provide those functionalities that helps us to manage array data. One extra benefit from your investigation of time to learn those operations is that Although there are many different types of toolsets to help users, because array data is universal in the business of data analytics, there are a lot of toolboxes, but the basic operating basic options of operating those arrays are shared by almost all those libraries. And what is more convenient is almost all such functions share the same kind of interface, even similar or the same function names, such as take the sum along some axis or along some dimension, or take the average, or take some subset of sub-arrays, stuff like that. Those popular libraries sharing the similar interfaces include TensorFlow, PyTorch, which are very popular deep learning technologies recently, MATLAB, and of course NumPy and R. So learn one piece of tools, you have access to many. Okay, so that's for the tool set. Well, to our problem, we want to make, if you remember, if you review a little bit about what is machine learning. What we want to do is to have something here. We want to build an algorithm that helps us to pick up one hypothesis from the hypothesis set and deliver it for future use. And in the previous tutorial, we have made explicit representation of this. So in case of perception learning, it would be like this. Depth, we will have a function, and this function, let us call that perception predict. I have this function name in my memory because I have practiced this a little bit before. When you typed it, it won't complete the function name for you. So don't worry about that, just type it all. And when you have this ready, the online IDE-like environment will help you to type it later. It needs to accept a parameter x. This x refers to whatever data has 5 attributes. Remember, 4 true attributes and 1 constant 1 attribute, dummy one. And it needs to return its prediction about its y value. That is, whether it is Satosa or versicolor. Let's see, if Satosa is -1, the versicolor is +1. Also, as a perception, it will use a perception to do the prediction. So it will need a set of parameters. This is a prediction. No, this is not exactly the learning. This defines one member here. Okay? Because you have to have those members explicitly defined before you can actually do any training optimization or picking up algorithms among those members. We can make it explicit that W is 5 vector CTOR that represents the 4 widths for the 4 attributes and the bias, and X is n times 5 array representing the data. So, excuse me. Now we want to calculate the pairwise production between the weights and the values of the attributes in each sample of X. Here we would use a convenience provided by the computation tool of NumPy, because both both W and X are NumPy arrays. So we can write it directly in this way. What this operator does, this sample multiplication operator does on two NumPy arrays, has been specified by the NumPy library. What we want to do here is something like this. We have an X, I need a pen, okay. We have an X array here. The X array has n samples, and each of the sample consists of 5 attributes. This is constant 1. We have 5 W weights, 1, 2, 3, 4, 5. This is just a 5 vector. What we need to do is to multiply this value to this value, multiply this one to this one, this one to this one, so on and so forth. So we first concern about the multiplication, and then we will consider how to do the summation. Okay. So what we want is an output array, which is in this way. This value of this output. Let's take a more general example. See, in the ith row, and the ji is in the range of from 0 to n minus 1, and the j is in the range of 0 to 4, because the index starts from 0. Okay. So the value of this production array, we would like this to be the X array ith row and jth column times the W vectors, the jth W vector. So NumPy is clever enough. It provides us a function of broadcasting, which means when it examines the dimension of X and W, it finds X has a dimension of n by 5 and W has a dimension of 5. Then it will interpret the array of X has n objects, each object has 5 elements, and W has a singular object has 5 elements. And we'll figure out that by doing multiplication, we actually want to do the pairwise multiplication of each object in X and the object of W, and we want to broadcast this operation to all n objects in X in this way. This is the broadcast dimension. So if we do this, we do X W times X or X times W. This is the point-wise multiplication is commutative. The output array will be this one, this as we expected. Let us have a test. Okay, say if we add we can insert scratch code. So this is for our, it's like a scratch paper. We can really do something as in the sandbox. That is to be an MP array, which is of 2 dimensions. Say that 1, 2, 3 is the first row, and 4, 5, 6 in the second row. Let's print A to see the effect. Now we have a 2D array, which is a matrix. One row 1, 2, 3, second row 4, 5, 6. Let's have another bay. That bay has 3 elements that can be correspond to the 3 elements in each row of A. Call that 1, 1, 2. 1, 2, 2 maybe. Okay. We also print its shape maybe to make this explicit. Let's print the result of A times B. Okay, see, the shape of A 2 rows, 3 columns. The shape of B 3. Look, the previous the corresponding row in A is 1, 2, 3, and 1 times 1, 2 times 2, 3 times 2. It becomes 1, 4, 6. Similar operation has been applied to the second row. Okay, that's exactly what we want a perceptron does in its computational step for a set of data points. So that is what we want. This and the sum because we want a prediction of each sample, and the prediction consists of the summation. We take the sum here, we then arrive a value. It's called hx0. The 0 would be there according to our previous convention. X1 do this. We'll have this value, and this h value is the sum of the productions. This is implemented super easily in NumPy. For such a 2-dimensional array, if you want to take the sum along 1 dimension and result in a value along the other dimension, you can just say this array provides us a function which is called sum, and the sum accepts a parameter. Its dimension, dimension is used in PyTorch and other library. In NumPy, it is called axis. So you can appreciate the similarity between different libraries. They just use a little bit different technical term, and then you can master them all. This is dimension 0, and this dimension 1. We take the summation over this dimension, that dimension to be 1. Okay. So let's choose this x1. Let's call it h value. We can make the code less cluttered, because x times w returns an array, and this array just provides us the function. as needed. So we do not need this intermediate variable. Good. And the next step for perception is to do something about this h value. If you can recall this, the prediction is +1 or -1 determined by the value. Okay, so NumPy, fortunately, NumPy provides us a very convenient function. We can just return prediction sign. That is done. Let us allocate any kind of W. Say I feel comfortable with this set. Maybe I remove the bias. Note now, because dummy variable, the constant one variable, is in the last element, so this one is the bias, not this one. Let's print the perception predictor. The result of the perception prediction on our training samples. 01 is uselessly legal. Okay, so let's do some sanity check. How about if we make a very negative bias? Say if the prediction, if you make a very negative bias, you will change the h value towards the negative side. And if can we, let's see if we can change the side of the prediction. -1 are reasonably useless. Okay, in the next video, we will learn how to adjust this w, therefore to implement this function of actually learning the perception. Before that, I want to give you a further caveat here. This sign function returns 0 when the value is exactly 0. This is extremely unlikely for any extra practical data, because it is very unlikely you have a random set of weights and some practical measurements. So that their combination, the sum of their production combined together arrives exactly the value 0. But although this is very unlikely, this construction is not watertight. There is a slight possibility that it's go wrong. When in practice, a practical data project, you need to do something to guarantee that it will never return a rubbish value of 0 prediction, because you only recognize the prediction to be -1 or +1. Okay.